Work it, make it, do it, make sense.
Okay, so let's start because there's not a lot of time. So hello everyone. So today we're going to solve Sudoku in Scala. So I apologize in advance, it's going to be fast because there's a lot to go through in 15 minutes. So just a quick introduction. What we're going to do today, we're going to solve Sudoku with using functional programming in Scala. Hopefully have a bit of fun and learn something. I'm not a Scala expert, it's just a hobby, so don't judge me. The original idea was from Scala meetup in London. It's not meant to be a fast solution to solve Sudoku at all, and it does not solve the hard grids that require backtracking. So I'm sure most people are familiar with Sudoku, but I'll still summarize. You have a 9x9 grid, and you have to fill it with numbers from 1 to 9, and there's only 3 rules. The first rule is that in each row, you need to have all of the number from 1 to 9 exactly once, and it's the same with columns and the squares as well, the 9 squares. So before we can actually solve the solution, there's no requirements for Scala in this talk, so I need to teach you the building blocks that we're going to be using. So the first one is the case class. So if I read this quote I found, it's a regular classes which export the constructor parameters and which provide a recursive decomposition mechanism via pattern matching. So it's a bit complex, but so let's use an example. So if we have a trait, which is like an interface in Java, and then I'm going to be defining my cases for that class. So you can think it as a bit of a like enum for classes. So if I have a shape, I can have 2 types of shape. I can have a circle and a rectangle. And you can see here the constructor bit that I just put a parameter d inside, and it will automatically create a constructor, a getter, no setters because everything is immutable. And now I can use the pattern matching. So if I define a method that takes a shape, and I want to do different things depending if it's depending on the shape, I can just do a shape match, and then I can have 2 cases, either a circle and a rectangle. So here there's a lot of things to notice. First, this is a bit like a lambda in Java, because when I'm doing circle d, I'm actually creating a lambda with this value d, and then I can do something with it. And also the thing to realize is there's no return statement in Scala, because the last line is the return statement. So here I'm returning that, and then I'm returning the string. So if I create 2 circles, 2 shapes, 1 circle, 1 rectangle, if I call the shape print method, I'm going to get a circle and a rectangle. So that's useful. The next thing I'm going to use a lot is the vector library in Scala. So it's a bit of a magic library, because you have a lot of libraries, collection library in Scala for immutable, and the vector is EC, means effective constant time across all of the operations. So it's fast, it works well, we just use it, it's for free. So this is something that we're all familiar with, maybe with the Java 8 Streams API. So for instance, you can have a filter function. So if you take a vector of type A, and you have a predicate, which is a function of A to Boolean, it returns a new vector, and it's only going to keep the elements on that vector that match the predicate. So if I have a vector 1, 2, 3, I call filter, and I check for the number to be even, I'm only going to get vector 2. That's as you would expect. The map operator as well, you might be familiar with the stream in Java. So if I have a vector of A, I can create a vector of B by using a function from A to B. So here in this case, if I have vector 1, 2, 3, I give it a function, a lambda that does times 2, I'm going to get vector 2, 4, 6. Here I'm not changing the typo, it's just a special case. We have the flat map, so I think a lot of people confuse map and flat map. So the difference is in the signature. In map, the function goes from A to B. Flat map, the function goes from A to vector of B, or if it was a stream, from A to stream of B, or if it was an option. And actually, it's true for every monad, but that's another story. So if I have a vector 1, 2, 3, and I have a function that returns from X returns a vector, if I were just to call map on it, I will have a vector of vector, but this method will flatten everything, and I'm just going to get a vector 1, 1, 2, 2, 3, 3. So the next one is the group operator, and it's going to be very useful for us later. So basically what it does, it's a chopping operator. So a Sudoku is a matrix, so I'm going to model a matrix as a vector of rows. I could have modeled it as a vector of columns. It's a completely arbitrary choice. So imagine in this example I have a smaller matrix, 4 by 4, and I'm going to define it. I have my rows 1 to 4, 5 to 8, etc. And my matrix is my vector of that. So it's a vector of int. So if I call the operator grouped by 2, it's basically going to chop that matrix into 2, and I'm going to get 2 matrices, the first half and the bottom half. And why we need it is because, as I mentioned in the 3 rules, one of the rules works on squares, so I will need to access all of the numbers in one square. So we can do this in a little trick, and we're going to be using a bit like a binary search. So imagine I number my squares from 0 to 1 on each side, and I want to access one square. So let's say I want to access row index 1 and column index 0, so this one. So in my binary search, I take my matrix, I chop it in two, and then here, and then I'm going to choose the half that I want. So here I want this half, so I chuck the first half. And now I want to cut the other way, so I'm going to be cutting the other side. I'm using flat maps. I'm going to take each row, so this one and this one. The row I'm going to take the row, group it, and then select the bit I want. So in this case, I'm going to get 9, 10, 13, 14. Because it's a flat map, everything gets flattened, and I'm getting one vector, 9, 10, 13, 14. So it's just a bit of a nice way to get the squares. Another thing that's useful in Scala is tuples. Very easy. If you want to return more than one thing, you just put them in brackets, and then you can really easily access the elements using underscore 1, 2, 3, 4, first element, second element, etc., etc. Another interesting operator as well is zip with index. So if I have a vector of anything of type A, if I zip with index, I'm going to get a vector of tuple of A and int is a position of the element in the vector. So here, if I have A, B, C, I'm going to get A0, B1, C2. The last thing I want to talk about is the transpose operator. So you might be familiar in the math. So if you have a matrix 1, 2, it becomes a 2, 1. If it's a square matrix, you flip the matrix around the diagonal. But in our example, so I've said that I modeled the matrix as a list of rows, but what if I wanted a list of columns? Well, if I just transpose, that's what I'm getting. So if I have a vector, let's say with 3 rows, 1, 2, 3, 4, 5, 6, if I transpose, I'm going to get 1, 3, 5, 2, 4, 6, which is basically a view of the columns. So I'm going to be using that later. So now we have all of the building blocks. We can start solving the solution, and we start by doing a data modeling. So Sudoku is a matrix of cell. So what's a cell? We're going to create a trait cell and use our case classes. And we only have 2 options. Either I know the number in that cell, in this case it's a fixed cell, or I don't really know. And so I'm going to call that an undetermined. And a fixed cell has an attribute which is the number I know, and the undetermined has a value, a list of values which are the possible number in that cell. So when I'm going to start my problem, when I'm going to pass my problem as a CSV, for instance, I'm going to create a fixed cell when I have a number, and I'm going to create an undetermined cell with all of the possible values from 1 to 9 otherwise. And then my problem is going to be a vector of cell. So I'm going to create then a Sudoku class, which is going to have one attribute, a grid, a vector of cell. And I said Sudoku has 3 rules, so I'm going to implement 3 methods. The first method is a value allowed in a row, in a column, in a square. And the signature is, well, I'm going to give it the position. So it's a tuple. The first one would be my row index, then it's going to be my column index. And then it's going to give, I'm going to test for a specific value. Can I put a 5 in that square? And it's going to return Boolean, true or false, depending if I can do it. So let's get started with the row logic. So how do I know in a Sudoku if I can put a specific number in a row? Well, I can do it if it's not been used already in the row. So what I do is I take my grid, using position underscore 1, I select the row that I'm interested, and then I just check, does it contain fixed value? And here, one of the smart things of Scala is that it will do pattern matching behind the scene, and it can check if it contains a type of fixed. So, and then I just use the negation. If it doesn't contain a number in the row, I can do it. It's very similar for the column logic, but I need to access the column. Well, we know how to do that. We have the transpose. So I take my matrix, I transpose it. So now I have a list of a vector of columns. So I can select my column using the underscore 2 of the position, and I just check if it contains the fixed value. The square is a bit more complex, but we've already done the work with this chopping with the group. So first I need to get the square index, this time from 0 to 2, by dividing by 3, the basic Euclidean division. So I take my grid, chop it into 3, my binary search. Then I'm selecting the band that I want. Then all of the rows in that band, I use a flat map. I chop all of the columns. I get the bit that I want, and then I flatten everything. And this is going to give me a normal vector with all of the values in that cell. And I just check if it contains a value. Now, to make it a bit easier, I'm going to make just one method that is going to wrap everything. So this method called isValueAllowed is just going to call all of the 3 methods in a row. And now, believe it or not, there's only one slide left for the solution, and that's the rest of the code. So I'm going to be explaining that. So this is a method of the class Sudoku. So remember, in Scala, we like to do everything immutable. So this class is going to have a method called filter, which is going to return a new Sudoku, and hopefully this new Sudoku will be progressed. I'm going to have made some progress. So how do I do it? Well, first, I have only one thing in the class. I have my grid. So I take my grid. So remember that all of the so all of the methods I have for the rules, they take this position. So I need to have my row index and my column index. So I'm going to do this by using the zip with index. So I take my grid, I zip with index. Now I get a vector of tuples with a row and my row index. So now I take my row and I zip with index again. And now when I do a map, this time I can access the column index. And when I look at my cells, so now basically I have a vector of cells with all my position. What I want to do, so when I know already the number, there's nothing for me to do, I can just stop. But when I find an undetermined cell, what I want to do is I want to replace it by another undetermined cell which contains less value. So if I reduce my problem statement, so that's what I'm doing here. Remember, there is no return statement because we're in Scala. So if I have undetermined cell values, I'm returning a new undetermined cell, but I take the old values and I'm filtering it, and I'm passing my predicate, which is my isValue_allowed function, with all of the parameters. And this is going to reduce all of the possible values in that place. And this is basically a catch-all. If I have anything else, just return the same. So this is going to reduce my values. And I'm going to reach a point where I might find some undetermined values that have a size of 1. So I can do a case, pattern matching with a guard. If this is the case, then I can transform it into a fix, and that will allow my problem to progress. And now at the end, this is the because this is a recursive function. So if my filtered grid is the same as my grid, it means I didn't make any progress for two reasons. Either I've solved the Sudoku, or it was a Sudoku that cannot be solved by logic. It means you need to do backtracking. So it means I just returned that Sudoku. Otherwise, I return a new Sudoku, and I call recursively the filtered method again. So that's it. I don't know how I'm doing with time, but you can check the code in GitHub. It's tested against 100 examples, simple Sudokus. I have 5 minutes. Oh, I went faster than I thought. I apologize for that. I couldn't see the time. So there's a bit more of passing the CSV and error handling and things like that. So I have time to take questions, which I was not expecting. I can bring back another slide if people want to, because it was... Which slide do you want to watch, to see again? I think that's the most interesting slide. Yep.
Did you find some solvable Sudokus that this doesn't?
Yes, because... so the question is, are there some Sudoku that are not solvable? Yes, because... most of the hardest Sudoku, you cannot solve them by logic. So this is called a CSP, a constraint satisfaction problem, which you can reduce using logic, by using inference between the cells. But you reach a point where you cannot make any logical guesses. So you cannot make logical inference. You need to make a guess, try it, and then you need to backtrack. So a bit of a weird, I've wrote a lot of Sudokus, and the one where I could solve everything was something like that. And then you couple it with a search algorithm, and then you have to find a heuristic to, when you make a guess, where do you make a guess? Well, maybe you make a guess in a place when you have the least number of choices, or then you can find also a place that has the most constraints, so you can terminate your problem early if you've made a mistake.
How does it deal with the case where the second undetermined value unlocks the answer to the first? So if I've got 3 empty fields, but I have to fill the third one before I know what the second one would be?
Well, in this case, it would just be, like the next iteration. But I mean, it depends if it's a case that you can solve by logic or not. I mean, as a human, if you can solve it by not taking any guess, then this can solve it. I don't know if I'm really answering your question.
in one step? Like it can set a value on a row and another one on the third row if it can detect it.
Yeah, definitely. Or so basically, if you kind of build like a big tree for this problem of constraints, you might have independent trees in each round. Like these cells, in this part of the Sudoku, you can make a guess. You don't need the other one, so you can make these guesses, and then the next round they will be available for people for other cells that need it. Yeah. It can do more than one. At the beginning, probably it's gonna, if it's maybe a hard one, it will make one, and then another one, and then towards the end, the more you fill, the more options you leave. Okay, I don't know how much time there is left. 1 minute, so one last question maybe. Shall I go back to a slide I went too fast on, which is probably most slides? All right, thank you very much.